comes out of Steinmetz's symbolic method. So we have a way of dealing with these things with arithmetic instead of differential calculus. The effects are massive on what you can understand you can gain by getting rid of these giant differential equations. Okay, let's keep going. Okay, and then basically 1 to the first power can be given as the absolute value. That's what the two bars indicate. And this is the absolute value of any of these 8 poles is 1. So basically, together, it's a unit. The whole thing operates as a unit. Ultimately, it's not separate. Okay, let's keep going. So we have, these are our basic poles. We have plus and minus 1 like on a battery. Okay, we have plus and minus J like between the coil and capacitor. We have plus and minus H, where it's capacitor going into the resistor, let's say. And we have plus and minus K, where these are oscillatory exchanges, where capacitor, resistor, inductor, and resistor exchanges both occurring. So we end up with waves that have, go back to the transient waves again, the oscilloscope type diagrams. These waves are represented by double movement, where these are just simply what are called single energy exchanges. These are double energy exchanges. And then later on we get into pairs of these and quadruple energy exchanges. Go back to the physical analogy of the automobile. No, let's go picture-wise, go forward.
Go forward.
Yeah. Okay, so this basically is our 8 poles, all of which have a plus and minus relationship. In other words, K has plus and minus, H has plus and minus, J has plus and minus, and 1 has plus and minus. So there's always opposition in the two forms. And these represent energy exchange. So if we want to look at a situation of energy exchange in practice, okay, as we explained, if you're in an automobile and your velocity changes with respect to time, then all of a sudden these secondary effects like electromotive force and magnetomotive force appear. So if you go down the road and you put on the brakes instantly so that the wheels, we're given a perfect situation now, the wheels come to a complete standstill instantly. Okay, and they do not slide on the pavement. What happens is the car wants to keep moving forward. This represents the magnetic field. The car wants to keep moving forward, but it can't. What happens is the tires start to twist, okay, which represents the capacitors. So now all the energy of the mass of the body, which can't go forward, but it's being pulled forward anyway, now is charged up in like a spring action in the wheels. Okay, which only can deform so far and they can't move on the pavement. Okay, so the car pulls forwards and charges up its energy, but now the inductive energy is all gone and is charged in the dielectric energy symbolically in the wheels. So what it is now the wheels, there's nothing holding them forward anymore. So what they do now is they pull the car back. As they pull the car back, they tend to restore to their original position, but at this point, now the car is flying backwards just as fast as it was going forwards. So what it does is now the wheels are distorted backwards in an equal amount, and the car moves backwards the exact same amount it moved forwards, and then again the whole process starts over, so the car, that's what causes the whiplash when you stop in the car. It's this oscillatory energy interchange produces, let's go back to our waveforms. Produces this. The energy's trapped, and the car will just sit there and bounce back and forth forever, but nothing's perfect. So in reality, we don't get an alternating current, we get an oscillating current. Now how does this come to be? What it is let's say you slam on the brakes, but now, as we know, the car will skid. Okay? Now, if we go by electron theory tells us that the car's not moving down the road, but the road's moving, carrying the car. Now we know that's a bunch of crap. The road doesn't move, the car moves, okay? But the relativist only sees the tire tracks and doesn't see the car, like the footsteps of the snowman, of the invisible man in the snow. The man is not there, because you can't see him. All you see is the footprints, and that's all that's real. But obviously that's not correct in our physical analog. So what happens is now, if the road does try to move, in other words, if the car slides on the pavement, it pulls the pavement forward with it, but the pavement lags behind the car. Now this is what the electrons do in the wire, and they get hot. The road gets hot and it makes a screech, okay, which is a disruptive type of oscillation akin to one of these type of situations. It's not a pure tone. It's a breaking, pulsing type of sound That's what gives it that horrible sound. So what happens is before the wheels can completely absorb all the energy, the car has slid forward and destroyed some of that energy, so the oscillation will die off like this. Now, if that rate of energy dissipation is so great that it can reverse, then we get what's called a deadbeat impulse. So the car basically lurches forward and then kind of comes back and comes to a stop. So this is basically the physical representations in physical world realities and everybody experiences on a daily basis. This is the type of dynamics we're dealing with. It is no more complicated than that, other than you cannot see the electrical phenomena, but you can see the car and you can see the wheels. Okay, let's keep going back to the nav. So these basically are just symbolic ways of saying these are the axes that we're operating in and the dynamics that result from it. It's no more complicated than that. It looks complicated, it seems abstract, but it's the ultimate simplicity when you're dealing with electric calculations. Okay, let's keep going. Okay, so we have our 8 relationships, and we saw on the previous page that we can take each one of these letters and associate with specific electrical waveform that's encountered in practice. Okay, we'll keep going. Okay, now I wrote a paper on this that I was going to present here, but there's no time for it because I have to warm you up with all the previous material, so we're just going to fly through it. But this is an example of the Steinmetz method. Let's just go from page to page. We start with the basic AC problem. Okay, we have a voltage across a resistor, and we have a voltage across an inductance coil, or a reactor, in this case, a reactance X. Now, if I add the voltage, if there's 1 volt across the resistor, because of the back EMF, and there's 1 voltage across the inductor, because of its back EMF, I do not have 2 volts as a result. Because I have to add these in a Pythagorean right-angle relationship. So instead of 2 volts, I have the square root of 2 volts. So basically, R and X, R in ohms and X in ohms exist, where this one exists in plus and minus 1, this one exists in plus or minus J. So this is the first use of this type of thing. So I would say R plus JX equals Z. Instead of R plus X equals Z will not give me the right answer. I have to say R plus JX gives me Z, and that's what the dot on top of the Z means, is that now it's a complex quantity. It's not a result of direct addition. But if I take these 2 quantities and square them, and take the square root of them, that gives me the length of this. And if I take the ratio and take the trigonometric function of it, then that gives me the angle. So this is the basic way that electronic technicians, not electrical engineers in general, electronics technicians tackle the problem in this manner. So let's go on. Keep going. Keep going. I'm not trying to talk about this. So we're going to represent this now. It's typically can be called 2 quadrature planes. In physics it's called, I think, orthogonal, or there's a name they use that not normally used in electrical engineering. Can you help me with that, Charles?
Orthogonal is the right word.
Okay. What's that?
Orthogonal will do fine.
Okay. So we have the plane of resistance and the plane of reactance, but in reality we can't really present it like that, because they exist in 2 different types of dimensional realities. One represents energy storage, and one represents energy dissipation. So basically, the reactance has real physical existence in a magnetic field, but the resistance works in a strange way inside the atoms and destroys or creates the electric field, but it's not the electric field. But we have to add these 2 quantities to get the total voltage in the circuit. So we need a better way of visualizing it. So let's keep going. So let's take this plane of paper, okay, and we take the one that's at right angles and we turn the paper, so now that one piece of paper is broadside to us, the other one, because it's infinitely thin, we can no longer see it. So we call that the resistance, okay, or the imaginary plane. And the reactance is real because it'll light a light bulb, which is the resistance. So we'll call that the real plane, and we'll give that area, which is the dimensions of inductance, length squared. So that is a real quantity. Now we'll go one step further with this analogy, and so we can work with it geometrically. Keep going, next step. Okay, being that these things exist in time, all these calculations are in time, we can't have a surface of time. Because time only exists as plus and minus, not multiplication. So what we'll do is we'll go take the plane and turn it again, okay, and reduce the resistance to what's called a weighted point. which has no physical existence in the equation, but is a point with weight. I think a guy by the name of Grossman introduced this idea in the 1800s. Okay, and we represent the reactance, which is the magnetic field by a line because it has magnitude, which represents the quantity of energy in the system. And this gives us a kind of dimensional picture of the problem we're dealing with, and this is what makes it hard to visualize and work with in engineering. So that's why we have the Steinmetz method, because we can't properly draw the diagram. Let's go back to the XR diagram. Let's go back. Go back. Okay, well, we can use this as a calculating tool. In other words, you can go into your electronics test. All you need is a ruler, okay? And you can measure 1 volt is 1 inch, and 2 volts is 2 inches, and draw a square, okay? And then measure that square, and then measure with your ruler, and get the voltage. I used to use this system in the Navy to pass the test, and I passed the test so quick by using this method instead of trig tables and slide rules that they accused me of cheating. Okay, let's keep going. But when you're a kid, you learn how to do things that maneuver quicker than they do in the adult world. Okay, keep going. We get some more pictures here. Okay, so these are basic alternating current representations. So if I start off, let's take the resistance R as our reference point, which is typically done in electrical engineering, because most of our consuming devices are resistances. They destroy energy. So they take energy out of the dimension, which we represented by this dimensionless point. Okay, now if I multiply by J, okay, or go around a right angle, okay, then this is what we call reactance. So if I go backwards in time by 1/4 turn of the rotor and the generator, okay, then in the time cycle, we've now entered reactance. Okay, now if I multiply by J squared, then we go around, then we have the opposite. I don't know what's going on with this thing. It's sure playing with me.
Put it in your eye.
Now it wants to go out. Something, oh, it doesn't like the black. Okay, so if I go around, so if I multiply quantity by J, I've gone this far. J to the first power. If I go J to the second power, okay, now we're at the point where the energy is being produced. Where here, the energy is being consumed. So if this is the resistor, or this is the motor, let's say, that's eating the power, then this part of the cycle is the generator, which is producing the power. Now, in any rotation of an alternating current machine, it must pass through all 4 of these cycles. So there's always a point in which a generator is a motor, and there's always a point in which a motor is a generator. There's no separating these things. So we have the JQ, then brings us to the 3rd rotation, and then J4 takes us back to J to the 1, and brought us right back to where we started from again. So we're developing a multiplication table. So we'll let this counterclockwise rotation represent the magnetic field, or the consumption of electrical energy. And then we have we'll do that in amperes and ohms. Okay, now let's go to the next one. Now we're going the other way. Now we're not using ohms anymore, we're using Siemens and volts. So now this represents more the capacitive side of what's going on. And it exists in the exact opposite, because this energy is always bouncing back and forth between these 2 fields. So now we have the conductance, and then we go around, and that gives us the susceptance of the capacitor, which is the inverse of the reactance of the inductor. And then we, this would be J to the -1 power, and then we have J to the -2 power, and that takes us backwards. We're producing rather than consuming energy. Then we have J to the -3rd power. It's dead.
Doesn't anybody else have one?
Okay, look, it works, but it won't work on the paper for some reason. It just, as soon as I start to use it, it turns itself off. It's got a little-
here.
it's got a computer.
And there should be one in the front of the big
Well,
bag.
I'll try to keep using it, but it's really frustrating. It's basically, it's got a bad switch.
It likes your face.
Yeah.
Watch it, you don't put it in your eye.
Okay,
Oh,
so,
it doesn't work here.
so we can see that with simple powers of 1 to some fractional power, we can use that as an operator to add these 4 poles of electricity together.
Can you repeat that again, please?
By using 1 to a fractional power, like 1 to the 1/4 power, as we've seen earlier, the 4 poles, or the 4 solutions to that power, represent each one of these 4 aspects of every alternating current electrical cycle. This is the S.F.T.S method of representing alternating current, so that we can add and subtract in these conflicting or quadrature or conjugate realities, like one being dielectric and one being magnetic, or one existing as a field and one existing out of the field, is these relationships. In order to add everything up in the equations, you have to have these operators that extend this beyond the original laws of addition and subtraction, because now we have to add in all these different forms that don't necessarily directly add. Okay, go to the next. Go back. So basically, in any alternating current cycle, we have the half where the magnetic force, where the amperes live, and we have the other half where the voltage or the potential and the dielectric forces exist, and these represent the watts or the energy exchange through the alternating cycle. In any alternating current cycle, the energy that's not being used by the power line is returned backwards through the power line back to the generator. It's a traveling wave type situation. If you don't use the electricity at the end of the cycle, it all thunders back down the power line and resyncs with the generator. So there's no energy lost in an AC system the way there is in a DC system. So this one's got a little game too. It goes on and then it goes off. So none of these things are useful. Let's go to the next one. Okay, so this is represented by, we have 2 situations, one of which we call the power factor, and one is what's called the induction factor. And these are the proportionalities between the total flow of electricity. The power factor is the amount of actual electricity utilized to the total amount of electricity in the system. That ratio is called power factor, and it's represented by the cosine of the angle of how we're moving around in the DLR. Complementary one is called the induction factor, and that is the ratio of how much energy is stored in the electrical system to the total amount of electricity in the system. So basically, A plus B, in some sense, is the total electricity. Okay, let's keep going. So this our generalized equation is any time function of alternating current, which is symbolized by gamma here. That represents a second-order differential equation. In this case, it's symbolic in the Heaviside method. Equals A plus KB. So we're using K as our most generalized operator. Instead of J, I usually use K in the more abstract forms, because J may grow out of it. So we can't add A to B directly, but we have to add them at right angles, as we've seen with R and X, in a Pythagorean manner. Now, this is where these conic forms come in, because we're working now where the planes, the angle of hysteresis is 0, and the planes are producing circular functions or alternating current phenomena. We haven't worked out of that yet. So let's go to the next one. And then these are our basic Pythagorean rules and our trigonometry to figure out where the angles are. So let's keep going. So this is our basic relationship. So if we go one step around, then this is our basic equation we use. So if I'm adding up the voltage in an electrical system and it has these phases, in other words, if that vector is on that part of the rotation of the generator going through its 360-degree cycle, that point is represented by this algebraic equation. That tells me where I am on the cycle and gives me how much electricity is being used to how much electricity is being stored. It's all inherent in this simple, basic junior high school equation. Okay, let's keep going.
Don't you need a square root there on the right-hand side?
Go back. No. That's on the right-hand side is a differential equation. That's a second-order differential. In other words, that's d squared dt squared. That's a symbol for it, but I don't want to start throwing calculus at people. So basically, we're dealing with a second-order function because we have 2 values, and we're in the dimensions of time because it's the number of percents of cycle going around, which is the cycle in per second, which is a time function. So the generalized function in time, which is gamma in t, in time, to the second order, okay, is equivalent to this. So instead of using a differential equation to describe this electrical situation, which is hideous and complicated, and really not defined, we can do it with the Steinmetz method and just have a basic, simple algebraic addition. So I have my 2, I have A on the bottom, as a length, and you can see the triangle that represents it. And then I have B as the vertical, and you can see the triangle that represents that. And the quantity of the two always have to equal that unity vector. These are our basic circle functions. I don't have much time to discuss this, I have to keep flying.
So the exponent is 2, not 1/2.
Yeah, squared. That's not x, that's gamma. That's the Greek letter gamma in the parentheses.
Alternative to the
Yeah,
laser
there
pointer.
we go. Okay. Okay, so let's, I'd like to have the time to really make it so people can understand this, but right now this is all for show. Because this could like make 10 lectures out of it. So I'm just flying through this so people can kind of see the symbols, and people that understand more can kind of see how this leads into more advanced mathematics that hasn't really been fully developed yet, particularly with regard to synthesizing energy and Tesla transmission. Okay, let's keep going. Keep going. Okay, so now we've gone from there around more. So now we've multiplied the equation by another quadrant or another value k of moving around. So I take the relationship and multiplied it by the operator, which moved us 90 degrees around the cycle. So now we have our voltage and current type things are represented by triangles now in another quadrant. And we keep going around the cycle. Let's keep going. These are the equations that are represented. So what I've done is I've multiplied my equation by the operator k, which has taken me around now 90 degrees, so now I start to have a new relationship which explains how the electricity adds up in that quadrant. Let's go one more step. Okay, so we start to get our mathematical table. So if I square this operator, it equals -1. If I take it to the first power, obviously it equals itself. So we're starting to develop a multiplication table to use in AC analysis, in the Simon's method. So let's keep going, keep going. Okay, so now I've gone around one more quadrant. Okay, now let's look at its equations. Next one. Keep going, we got an equation. So now what I've done is I've operated on our basic relationship with k to the second power. In other words, now I've gone around one more. So this multiplied by this, now I've gone into the third step of rotation, and that gives us another multiplication table that k to the third power is also equal k to the 1 power, actually should be -1 power, or -1, or minus is minus k to the next. So basically I can take all these and still turn it into a kind of plus or minus in my multiplication table. So let's go to the next. Keep going. Now we've gone one more quadrant. Okay, so now I'm starting to get another pole, so let's go to the equation. Okay. Keep going. Okay, so now we have if k to the fourth power equals +1 or k to the 0, so now we're starting to come back around the cycle. We're starting to sum up where we originally were. So let's go to the next step. Next step, keep going. Okay, so this is our basic relationship. As we move around the cycle, we use the interrelationships between these two quadrature quantities, this direction being symbolized by the number 1, which of course is not there, because 1 times anything is 1. But then this one is prefixed by the letter k, which means no more than the thing is at right angles to 1. And the sum of these two on a Pythagorean basis gives us the actual point on the cycle, and then the quantities we're dealing with in their relationship. And this point is represented by that differential equation symbol. So that's where we are is represented by that point. In other words, that's our differential equation of motion. Okay, keep going. So these are more going through the cycle. Keep going. Keep going. I'm not going to read it. Okay, now we're going backwards. So remember there was two. There's one cycle that went forwards and one cycle that went backwards. Just race through these. It'll be the same type of thing, except now it'll be in the denominator instead of the numerator because we're going backwards. Keep going. Keep going. So what we have here, we developed the mathematics where we're talking about an axis of rotation. So instead of using vectors or differential calculus, we're using what are called versor operators, where basically k represents an axis that we're rotating on, and every power of k, if we take k to the 0, we're at start. If we take k to the first, then we move 90 degrees. If we take k to the 2, we move to 180 degrees, we take k to the 3, we move to 170 degrees, we take k to the 4, we're back to 0 degrees. So basically, k is a logarithm to the base 4, but we're using a new type of logarithm now. It's not like the normal logarithms they teach you in school. Okay, let's keep going. So this, well, go back. So this basically is, we have k to the base 4 as an operator. No more. It's not like an algebraic quantity. There's no quantity. The quantity is only 1. It's a unit. But we raise that to a power, and that power tells us where we are on the clock dial. Basically, because they call clock diagrams in alternating current. To draw all these diagrams is hideous for your calculations. When you can plug it in with simple plus and minus equations, addition, subtraction, then all of a sudden you can see things that before would just be too tiny on the graphs and you couldn't measure with the rulers. Okay, let's go from there. So we start to develop our multiplication tables out of this. So we get all our poles. Keep going. What? Yeah, so these are our more generalized equations, so we can start to break it down mathematically, which we don't have time today. Keep going. So we get our definitions, which we saw earlier. Keep going. So these are our 4 poles. Okay, keep going. And then we start to develop our multiplication tables. So in a generalized sense, then we could move through these cycles over and over and over and over and over again with a more advanced type of exponent. And then develop further. Keep going. Keep going. Keep going. Go back. So this becomes our generalized equation. These represent the 4 poles of alternating current. So if I have resistance, I have conductance, I have magnetic inductance, and I have dielectric susceptance. Each one of those voltages or currents or powers or energies will reside in one of these poles, and I have to add them to this system of complex addition and multiplication in order to calculate this stuff with general, high school mathematics and no calculus. That's what all this is about. That's what made Steinmetz famous. All the hard stuff all went away, and this is just basic stuff that anybody could learn in grammar school, basically. I taught this stuff to my sister when she was in the 8th grade. Okay, or 6th grade, I should say. Keep going. So these are our basic, as we go through the power, then we have our familiar J and -1 and +1. But we're going to go beyond that now, so we don't have time to really reside on that. But these are the values we get as we move through our poles. Our 4th power, our base 4 operator. So the first power gives us -J, second power, and then multiplication and division, we keep going. So if we divide, this represents 1 over k squared, and that also equals k squared. So we start to get an interesting relationship where a quantity divided into 1 equals the same quantity multiplied by 1. Keep going. So we just worked through all this in forward, reverse rotation. Keep going. And then some more, representations of this, what the mathematics people need. So you define your terms. Keep going. Then this can be expressed also trigonometrically, which is the very thing we're trying to avoid, because then you have to use sines and cosines tables. Keep going. We can get into these are all trigonometric. This is the way this stuff is normally dealt with, which is way too complicated in your trigonometry they teach you in high school. Then we can resolve these things into infinite series in order to get the numbers without the tables. This is all basic trigonometry raised to the base e's. These are all your normal processes you go through to define your mathematical relationships and take them back to the definitions of the terms, which are all based on what are called infinite series. Okay, now we're going to expand this out. Okay, now what happens is when I was talking about this cylinder, which had variations in it with respect to time, these are Steinmetz's curves that he made on machines that were starting to produce energy anomalies. And what we have here is a situation where there's a wave in the wave, or we would call a canonic wave, like in music, where one melody, but then another melody will start later, in another time, but the harmonies will match up by some strange formulation that the musician has to create, so you can have 2 of the same pieces of music occur at a different time, but still be one music. The wave in a wave type situation. So Steinmetz found that the sine waves went away, and started producing these asymmetrical energy exchanges, and the law of conservation of energy started to break down. So normally, this would represent the pressure, temperature, volume situations in a cylinder. If an air compressor, let's say, where there's no combustion or energy being delivered into it. But this would be the curve if now we took the air compressor and converted it into a gasoline engine, where we still have the valves and cylinders, but instead of putting air in, we put diesel in it, let's say. And now it's a combustion cycle. As it goes through the cycle, okay, instead of the normal progression, we're dealing with this exchange.